All right, let's get going. So we are to mid-year week. I hear it's a rough week for a lot of people. Raise your hand if you would really want me to extend the project deadline till Sunday. A couple people are like, no. I might do that. You might convince me. I mean, I don't really see why not, to tell you the truth. It's not like I'm going to get a chance to start grading it this weekend anyway. So I think that's probably appropriate. Here's what we're going to do today. And by the way, look, if you haven't started homework 3, you're getting late, because it's not a short assignment. For those of you who have done most of it or finished it so far, it takes a little bit of time to get your head around, right? Yeah? People are like, yeah, no, we just put it together in 2 minutes. No, it's not. It takes a little bit more time to get together. So if you haven't started yet, I strongly suggest that you're already late. But get going on it. So we finished grading homework 2. There were a lot of people who had, well, I already said there were 75% of people who had some memory leaks of some sort. I've got to figure out how, well, I'll have the grades back either tonight or tomorrow. But you can see how you did. And maybe we'll work something out where you can fix memory leaks and so forth. But I'm not making any promises quite yet. Mid-year is Wednesday. It will be graded. It will be proctored by like 4 TAs, because I'm actually not going to be here. Here's the deal with that. You can ask the TAs questions on things, but they're going to come in and they're going to give it to you. I've instructed them that if they see anybody looking at neighbors, just to take the paper away, and then you can complain to me, and I will probably take their word over yours. So keep your eyes on your own paper. I mean, literally, they're just going to walk up and go, "Foop," if they see you like looking on a neighbor's paper. So keep your eyes on your own paper. Not to stress you out or anything, but I don't want any cheating. We'll talk a lot about mid-year today. So any questions you have, I will answer today about the mid-year, about what it's going to be like, what kinds of questions there are on there, and you'll get all that answered. It is not a, well, so I gave it to a couple people to look. I gave it to a couple people to look at the mid-year, and they, one person said, hey, there's a lot of coding on here, and then the other person said, hey, there's not that much coding on here. So I think it must be just about right. So as it turns out, I think it's probably OK. We'll talk all about the details about that. Questions so far on homework 3, while we're thinking about homework 3. What kinds of questions do you have at this point? About the data structures, about the way you add a student, remove a student, drop a student, et cetera. Anything right now you can think of? Now's your chance. Yes, Erica. I'm Julia. I'm sorry. I got the right. Sorry, Julia. Yes. Erica, right? Yeah, OK. Sorry, Julia. Yeah, go ahead.
If we make a temporary queue within a function, we don't have to delete anything, even though there's a queue array within the queue that the destructor takes care of at the end of the function?
Yeah. So Julia's asking a very good question. In fact, we're going to go over some memory leaks and how to avoid them. But Julia asked a really good question. If you do the following, if you say something like this, OK, queue, temp queue, right, like that, did we use the new word, a keyword there? No. So what this does is this creates a queue on the stack, which is perfectly fine. And you can enqueue and you can dequeue and all that. At the end of the function, when the function ends, the destructor for queue will take care of removing anything that's left in there. So yeah, you don't have to do any deleting there yourself. Like, it will take care of it just by the function ending. And we'll probably spend some good bit of time today talking about the details of what's happening under the covers there. Not specifically for temp, well, maybe specifically for temp queue, but yes, that's right. OK, so we'll go over more memory information a little bit later. OK, good question. Other questions? No? Let's see how we go on the memory leak stuff. And if you have more questions that crop up there, we'll get to that. OK? All right, so first things first, we'll do a little UNIX tip of the day. It's on the zip command, which is, you find yourself using that at some point. Then we'll talk about memory leaks. Then we'll do midterm comments on all about the midterm. OK? All right, so here's the UNIX tip of the day. It's on this function called, or this program called zip. Now, most of you have used zip files at some point or another, right? Well, it turns out that in Linux, there's a program called zip that you run from the command line, and it will take files and actually compress them and put them into one zip file, like you might imagine. So what you can do, raise your hand if you run out of disk space so far various times because of maybe core files or something like that, right? Did anybody check in their comp 11 folders and see that some of your projects had 40 core files in there, right? Well, it's probably because when you were running those projects back in comp 11 days, you didn't delete those core files and they're taking up space. So what you can do is you could actually, if you wanted to, say, store your comp 11 files in a compressed format so that they don't take up that much space, you could zip them. And here's how you would do it. Let's say your comp 11 is on the desktop. You have a comp 11 folder. You can change directory to the desktop, and then you can run this file or this program called zip, and it would be zip-r. What do you think the -r stands for? Recursive. Yeah, this is a recursive program that goes through all the directories and takes all your files. It keeps the directory structure, takes all your files and compresses them. You could do comp11.zip and then comp11/star, meaning all files in that folder. Zip them all. -x means exclude files that have core in them. So that would actually not zip up those core files. Once you have the zip file, you can then say rm-r comp11, and that will delete everything in comp11, but you'll still have your zip file. That will delete all those old core files. So that would probably save you a bunch of disk space just by doing that. Once you have that zip file, you can either leave it on the server, or you can SCP it or copy it to your own computer. And therefore, you'd be just fine with having it forever. Then when you're 20 years from now and you go, oh, I want to go back and look at my old comp 11 code, you can do that. Any ideas how you would unzip files? Max? Unzip. The unzip command. You just type unzip and then comp11.zip, and it would unzip all your files back into the original folder structure that you had. OK, questions on that? Yes, Isabella.
Don't unzip them. Is that bad?
If you want to access them, you have to unzip them. Yeah, you just unzip them and put them back in there. There are actually GUI programs for your Mac or for your PC that will allow you to look in and just get the particular ones you want. But once they're in the zip file, you're probably not going to want to look at them for a while.
So it would be unzip in that same line?
No, it would just be unzip comp11.zip. And it would go whoop and unzip the whole thing for you. Yep. Yeah?
Will you have to put in the recursion command again?
No, unzip will unzip the whole thing, and it will recreate the directories as appropriate. It keeps that data too. Yep. Other questions on that? Good. For some reason, I thought you could do -x and then just core star, and then it would just get the ones that started with core. It doesn't seem to work, and I don't know why. But anyway, star core star seems to work, and that'll do it. Any ideas, Max?
It depends on the shell, but if you don't have any core files in your current directory, you might just say no files found.
Oh, that's.
You might have to escape the stars.
Yeah, you probably the star. I'm not sure exactly. That's a good point. But anyway, that one works fine. So I believe that one's, in my tests, that line works fine. OK, other questions on that? That's the zip command. OK, let's talk about memory leaks. So I put a little post on Piazza that said somebody gave me some anonymous feedback, and the anonymous feedback was, please do some more talking about memory leaks and memory management in class. And the poll was, hey, does anybody else want to do this? About 75% of the people who responded said, please do some more. So we're going to do a little bit more today. Only 25 people actually responded, so it wasn't a full, not that many people responded. But we're going to go over this a little bit. And hopefully by the end of this little discussion, we will understand a little bit better about what causes memory leaks and how do we avoid them, and what does it actually mean to have a memory leak. OK? So yeah, go ahead, Isabel.
For providing homework 3, I noticed that it checks Valgrind, right?
Providing homework 3, I left the Valgrind checks in there, yes.
OK, so we don't have to do it ourselves separately?
Well, you should, but I mean, when you're running your own tests, you should probably run Valgrind anyway.
Right, for our own tests.
For your own tests, yeah. No, the ones we do, you don't have to run them yourself, because I left that in there. And this project will probably have many fewer memory leaks because there aren't that many places where you can actually have memory leaks, as it turns out. But we're still going to run all the tests anyway. So that's that. Look, what is a memory leak? Somebody give me their definition of what a memory leak is. What do you think? Graham?
Memory that you lost access to, but it's still allocated.
That's good. So Graham says memory that you've lost access to, but that's still allocated. OK. Let's try to come up with a little example here. OK, so that's a pretty good definition. How do you lose access to memory? What does that actually mean? Like, what does it mean to lose access to it? Max?
You allocate something, have a pointer that points to it, and then change the pointer.
Yeah. So remember when we were doing linked lists? OK. All that time 2 weeks ago, right? You had some linked list here. Oops. In order to make each one of these nodes, like when you start out with a linked list, when you start out with a linked list and you say, I'm creating a linked list, what's head point to? Null, right? It means there is no linked list. There are no nodes yet. OK. It points to null. When you want to insert a node, how do you actually create that node? Not trying to insult your intelligence. We're just going over it. How do you actually? Yeah, you make a new node. So you say something like node pointer new underscore node equals new node, like that, right? OK, that new command right there says to the memory system, give me enough memory from what's called the heap. Don't need to worry about that. But it says, give me enough memory that I can store a whole node. And have the pointer called new node point to that new node. OK, that's what we're doing. So it says in memory, give me this node, boom, right here. And then you set the head to point to it, and you set the next to null and all that, and you do all that. But this is the part that says, give me the memory. So for this linked list, how many times did new get called? 3. If we didn't do any deletes, it removes. But yes, it got called 3 times, which means at some point in your program, how many times do you need to call delete? 3 times. Now, the key to that statement there was, during your program, you have to call delete 3 times in order to get rid of those 3 nodes. Where do we normally delete all the nodes in a linked list? In the destructor, right? You've got the destructor, right, which was, in this case, I forget what it was called, for the linked list, right? List, linked list, right? You've got the destructor, right? And in the destructor, you have to walk through the list somehow, go to each node and say, delete that node, delete that node, delete that node. OK? That's if we just created 3 nodes, ended the program, the destructor would get called by the compiler would set it up so the destructor gets called, and it would delete those 3 nodes. Good. In what other case might we need to use the delete word on the keyword on this? When do you think? Talk to your neighbor about it. Say, hey, look, when do I delete this? When else in this linked list would I delete it? What do you think?
When you remove a node.
Yeah, if you have a remove function, right? Remove node n, right? When you call that remove function, OK, if this is the node we're trying to remove, this one happens to be the end node, right? We have to find it. What's the important part about when we're removing? What else do we need to keep track of? The previous one, right? We need this one because we need to be able to do this. Remember, we set the previous next to be equal to the one we're trying to remove's next, right? That repoints this guy over here. And now, if we're not careful, as Graham said, we will lose control, or we will lose, what did you say? What was your term? You said you lose access to this if we just left the linked list because nothing points to this anymore, right? Right now, like some current or something would point to it, right? curr, the current would point to this. Now you have to delete this because later, when you get to the destructor, it's not going to get removed because it wouldn't be pointing to this one. OK, so we insert 3 times. We call the remove, and we delete this one. How many times does the destructor call remove? Twice more. OK, do you get this? It's all about accounting in this case. We've got 3 nodes. At some point in our program, we have to call delete on every one of those nodes. Sometimes we call it when we remove the node. Sometimes we wait until the end of the end of whatever function is using our linked list, and it gets called in the destructor. Does that make sense? OK, so now when you think about any time you use new, you have to think, OK, when is this going to get removed? OK, it could be in the destructor, meaning I have to write a destructor to actually do it. Or it could get removed at some other point when I'm removing this piece from the whatever structure. OK, does that all make sense? OK, so that's the bottom line on memory management. OK, when do they occur? When we have new and don't have an equivalent delete somewhere in our program. When do we have to, and what do we have to do to ensure they don't happen? Keep track of all of the elements. This will get really hard. For our last project in here, we have a project where you're using, like, you might be using heaps, but it's a lot of pointers. And if you don't keep track of things, it gets really tricky to have no memory leaks. Like, I had to write the program like 4 times before I realized, oh, I've got to take care of these other things in a very special way. We'll get to there, though. Yeah, Cecily.
If you're making a temporary pointer within a function just to refer to inside that function, will it be taken care of?
OK, this is another very good question. OK, let's go back to our original. Let's just go back to our original picture here, where we had 3 nodes. OK, and the head points here. Now, many times what we will do is we say something like node star current equals head. OK, what did we just create by saying this? This is a key question right here. By saying node star cur equals head, this part creates what? What do you think? Yeah.
Pointer to a node.
OK, it creates a pointer. Is that what you're going to say? It creates a pointer to a node. Does it create a node? No. So this statement right here says, I'm going to create a pointer. That pointer happens to reside on the stack. For what it's worth, the pointer is on the stack. But when we say this, where does current now point? Wherever head pointed. So in this case, it points right there. The head also points there. This one points there. And so that's it. Now, when we get done using current, if we said delete current, what would that mean? It would delete that node. And we probably don't want to do that, right? Unless we're in a remove function where we're trying to do that explicitly, right? The delete function says, whatever the variable points at, go delete that. Okay? There's another, like we use this other example a lot when we do the expand function for dynamic arrays, right? Remember how the expand function works? First thing you do when you're doing an expand in a dynamic array is you say something like, let's see, what was a good example? So let's call it array, right? They've got some array. We'll call it an int array. Actually, we'll call it an int. We'll do it this way. Int new array equals new int, right? New int, and then we say how much we want, right? Like the capacity times 2. OK. Sorry, I forgot the star in there. Int new array, new int. Did we now request new memory from the operating system? We did. OK, now we've got this. So here's what we've got in a dynamic array. We've got the original array. Now we've got one that's twice as big, right? And we're going to do what? We're going to copy them. And that's that like loop. And then we copy them. What do we want to do to this one? Delete it. Array pointed here. New array points here. OK? What are we going to say to delete this one? Delete the brackets, and then ARR. So we're going to say, we're going to do the copy. I won't do the whole thing. We're going to do the copy. Then we're going to say delete bracket ARR. Does that delete the variable ARR? No. It goes to what ARR is pointing at and says delete it. OK. Then we say ARR equals new ARR. And now where does ARR point to? This one. Some people want to say delete new ARR. Is that correct? No. What would that delete? Do the one we just created. They both point to that. Delete does not delete the actual variable. It deletes whatever that pointer is pointing at. OK? Key concept. Very key concept. OK? Yes?
Just a question.
Yeah.
I know we're not supposed to, but if you got rid of the brackets, would it delete the pointer? Or?
No, it would actually not really. It would probably crash. Say some memory, or it'd probably crash. If you didn't have the brackets there, it would probably crash because it doesn't know that it's waiting. The only time you can delete an array, like you try to delete what's at that pointer, and it says, I never gave you one variable there, like one piece there. I gave you an array there, so I'm gonna crash. So that's what happens there. OK? All right. So that's a key question, like how we actually go about doing this. OK. Does that answer your question about thing? Does that answer some other questions about memory management? OK. I mean, I've gone over it a lot of times, but it takes a bunch of times before it sinks in sometimes. OK. All right. So there were some questions on Piazza about homework 3. In particular, about the temp array. I think we mentioned a little earlier, right? But in some cases, you can say, or not temp array, temp queue. When you're, step back a sec. So there's a reason that I've made this homework 3 assignment not efficient. It's so that you get used to like in-queuing and de-queuing. It's not efficient. Like if you were going to make a program, you wouldn't want to use a queue the way you'd want to use a queue like that has the ability to like go through individual items and things. You wouldn't want to just be able to, especially if you're going to drop a student or something like that, right? Or remove a student from the wait list or whatever. But I did it this way so that you have to think about, oh, OK, I can dequeue from the queue and in-queue to another queue and dequeue back and in-queue into the original queue and so forth. But what I did in here was I said something like queue, right, temp queue. And this is exactly what we talked about earlier. This creates the object, right? And you don't actually need to do any deleting on it later because we've already created it. Like we've created it inside the function. How long does this queue last for? Just the function that it's defined in. Could you do this? Could we say queue star temp queue equals new queue? Could we do that? Sure. What would that do? Actually create the memory, or well, request the memory from the operating system, give you the space for a new queue, and say, here's the pointer to it. But at the end of the function, what would we have to do to the temp queue? We would have to delete it, right? You'd have to say at the end, delete temp queue, right? Or underscore, whatever, right? You'd have to say delete temp queue. That's how you'd have to do it. Yeah?
You created that, but it wasn't actually a temporary thing. You wanted to keep it for the rest of the program. Could you do that?
Yeah, if you want to keep it for the rest of the program, for whatever reason, it probably wouldn't be called temp queue. But if you wanted to do this, yeah, it would stay for the rest of the program if you didn't do the delete. And then hopefully in the destructor, temp queue would get deleted by a destructor, right? And let's see, it actually should. If you did this, it should get deleted by the destructor eventually anyway. So you wouldn't have to explicitly delete it. But if you did, that's fine. OK? Yeah. Actually, let's see. Would it? I don't think it would originally, or if you didn't do that. OK, other questions on this? OK. All right, keep this in mind. There's been a lot of Piazza posts about that. So if you, in the assignment, if you get to the point where you're like, why am I seg faulting, go back and look at some of those some of those questions from Piazza, and you'll probably get some of them answered. Or come to TA office hours and we'll help you out. Speaking of TA office hours, if for some reason you get to office hours and there should be a TA there according to the schedule, and there's not, let me know so I can put the hammer down on them. Right? They're normally very good about attending office hours, but sometimes things get mixed up and they don't go and they should, and I don't want you guys to be like missing out because they should be there. OK? All right. Let's see what else on memory leaks. Cause when we use new operator, we've already gone through this. We do not delete that memory when the program is running. The dirty little secret, by the way, is when your program ends, the memory will get released back to the memory system regardless of whether you do the deletes. But let's say you have some sort of situation where you're doing InQ, DQ, InQ, or I don't know, insert into a linked list, remove, insert, remove a billion times, and you never delete on that remove. That's a memory leak. It just starts wasting memory. OK, and that's what you want to avoid. Yes?
So when you do create like dynamic memory, at the end of the program, does the pointer gets like?
Yeah. So the operating system is smart enough to know it keeps track of everything that your program allocates, right? And then it says, OK, even though you didn't do it, I'll take care of it for you. Boop, and it gives it back. But we want to avoid that because we want to clean up after ourselves. That's really the big thing. And if you don't do it, you'll end up with these real memory leaks where your program keeps growing in memory and out of control. You don't want to. You want to avoid that. Yeah. OK. Good questions. All right. Let's see. Every time you use new, you have to think about when you'll use delete. Bookkeeping, right? It's all about bookkeeping in this case. If your data structure is being deleted, like at the end of the program, the destructor will get called. And the destructor is where you walk through the linked list and delete things, for instance. OK? All right. Let's see. We've already kind of talked about this. In a linked list function, if you use new to create nodes to insert, when do you need to delete those nodes? Two cases. When did we say? In the destructor, or when you're removing it, like in a remove function. That's that. Good. Other questions on memory leaks? Yes?
So we can, when we have the option of either declaring a queue within a function and then using it,
Yep.
or creating a new one and then deleting it at the end, like what determines which of those is better?
Yeah, that's a good question. If you are doing a structure that you know will only last for the duration of your function, there's really no need to worry about like doing the dynamic memory. You just don't need to worry about it, because why bother deleting at the end if it's going to happen anyway, right? If you want it to propagate through the rest of your program after the function ends, you have to do this, right? So it's like in the expand function. You couldn't say, let's see, well, that's not the best example, but you couldn't say something like int star. It's not a good example. You can't, but you can't say something like, I don't know, int new array bracket capacity times 2 or something like that. First of all, it wouldn't work, but if you wouldn't want to do that because you need it to propagate through for the rest of the program. Yeah.
Why can't you do that if you don't want it to propagate? Why can't you do that?
You can't do that because the compiler actually doesn't know what this means. Unless if this is a defined amount, then you can do that. But if this is a variable, see, the thing is, variables, like when you have amounts for arrays, the compiler needs to know ahead of time how much space to allocate. Otherwise, it can't do it dynamically. Like it would have to do it dynamically itself, and it can't do that. So you're not allowed to do that you're not allowed to, unless you know the actual number. Or if this is a defined, like if this can turn into the number 50, then you can do it. But if it can't, like if it's some variable a or something, you can't do it. Or if it's capacity times 2, you can't do it that way. It just won't. It won't let you because it can't figure it out, and it needs to know the actual amount beforehand. We're getting a little into the weeds, but yeah, Julia.
Is there any time when you have a memory leak when you haven't called new?
Not in the way we're like writing programs. No, there might be some other ways you could possibly do it. But no, if you're not using new, you're not going to have to worry about memory leaks.
I have a memory leak in my program and I didn't use it.
You didn't use it. Well, are you sure that you might want to look? Maybe I used new and you used something that you didn't do it quite correctly in the way, and then that might have been it. Like in some of the other helper or the other classes like set or queue, there might have been a new in there that you're not paying attention to. Or remember, like in your queue, there's an expand method, and you have to use new there. So you just look through all your things. You probably had to use a new somewhere. If you didn't, maybe something else is going on. But I'd be happy to look at it later if you want. OK? All right. Anything else on memory? Does that help a little bit, like getting your head wrapped around it? If it doesn't, there's lots of stuff online you can look at. Like you can review the notes and review the programs, and there's lots of stuff online that tells you about this stuff. OK? All right. All right. Let's talk about the midterm. So if you're in Comp 11, this is probably familiar. You're allowed to use a one-page back and front handwritten set of notes. Handwritten. Don't try to type it and like bring a magnifying glass or something because you use 2-point type. Right? I was telling this story earlier. There's an urban legend about a professor who said, anything you can carry into the room you can use as a reference. Right? This is before like your iPhone, right? And some student came in carrying a graduate student. Like, sat him down next to him. You know, why not, right? And carried in. The letter of the law instead of the spirit of the law, I guess. So how should you go about studying? Well, you should pay attention today. We're going to go over lots of stuff today. Review the slides. Review any notes you took, obviously. Code samples, videos. There's lots, all the stuff that we've talked about. Like you can go back and look at virtually the entire class if you wanted to. You probably don't have time, but you could do that. Good idea to go read over homework assignment 1, homework assignment 2, all of the labs. Just read through your code. It doesn't take that long. Just read through your code and go, oh yeah, I remember doing this. Oh yeah, this was the tricky part about, using a stack or recursion or whatever. Okay, review that sort of stuff. Let's see, read the labs, homework assignments. Yeah, those are the big ones, I would say. Okay, not too much else that you can really do outside of that. You could read the book. I mean, I guess you could read the book. I just got an email from the bookstore saying there's still copies of your book on the shelf, and we're going to change to the next semester. So have your students come buy it. Trying to get you to buy more books. But if you haven't bought the book yet and you want to, still at the bookstore. What kinds of problems are we going to ask on the test? Well, there'll be short answer type questions, right? And if you saw the last semester's test, it's very similar. It's going to be in like types of questions. The questions will be different, but types of questions. Short answers like explain a case where using a linked list is better than a dynamic array. How would we answer that? Linked list better than a dynamic array. Are there any cases where that's the case? What do you think?
When you have to insert things, then it's more efficient to use linked list.
If you have to insert, in particular, where? In the middle, maybe, or even at the beginning, right? Yeah. What are you going to say?
Oh, yeah.
Same thing. Yeah, at the head. If you remove it at the tail, it's for a link for a dynamic or for an array, it's pretty easy, right? You might still have to expand, but it's pretty easy. Yeah. So answering questions like that. Finding bugs in the code. OK, this tends to be pretty tricky. Right now, you have to do that in your own programs all day. But when somebody else writes something, it's sometimes tricky to find the bugs in the code. But what kind of bugs am I talking about? I am not talking about like a missed semicolon. Right? Like I'm not talking about syntax type errors. Don't like going on, oh, did he put the semicolon in the right place? That is not what I'm looking for. Right? I'm looking for like legitimate things that most of the time will not cause a compiler error, because those would be easy to fix, right? I think there's probably one example on the test that it would probably cause a compiler error, but it's also a pretty easy one to find. But other ones, like things that won't cause a compiler error but might seg fault or might be an off by one error. You guys know what off by one is, right? Like you're going through an array, or you're going through a for loop, and you've screwed up the beginning or the end. You don't know which one, haven't started on the right ones. Things like that you should look for. You should be able to read the code, figure out what it's supposed to do, because I say something like, insert in the middle of a dynamic array or whatever. And then you should be able to figure out what it's supposed to do and then read the code and say, is it doing that? Those are the two kinds of bugs. The hardest bug to find is the missing part of the algorithm. Like if it's not there, it's hard to notice that it's not there, right? Unless you really know the algorithm. So you do have to study these things so that you can remember that. But those are the kind of bugs we're going to have. Yeah. Yeah. What I'll say is I'll say there's bugs in here. Find them and fix them. And I'm not going to make you play like how many bugs are there, right? I'm not going to say this program has bugs, fix them all. I'm going to say this program has 4 bugs or 5 bugs or whatever. Find them all, right? So it's not. I'm not trying to trick you on this, okay? I mean, this test is not one of those like I'm trying to trick you type tests. I would love to give everybody 100 on the test, right? And I'm sure there will be hundreds. Actually, there will probably some 104s because there are 4 bonus points. If you were in class or if you've been watching the video, I gave some bonus questions based on stuff we just happened to chat about in class. It wasn't necessarily on the syllabus or whatever. So should be, and those are tricky sometimes. Like those are like, aha, I'm trying to trick you. But too bad. They're bonus. Question. During class time. Not outside class. No, I didn't ask any bonus questions that are like from outside class. Oh yeah, the test is during class. Come here during class. Don't look at anything but your paper, etc. Bring your ID. I'll probably have the TAs walk around and check your ID so you don't cheat. Let's see. What else? Question?
Do we need like a variety of dictionaries?
Oh, well, so you can bring the back and front page. You can bring, if you want to bring blank paper, that's fine. But I think I'm going to have the TAs bring blank paper for you. I mean, I'd rather not you have like a stack of papers. I don't want them to have to like look through it. You're not allowed, you can use a calculator, but don't bring like some like QWERTY keyboard programmable calculator that you could type all answers in and stuff. You're not allowed to use your phone as a calculator. You're not allowed to have your phone out, all that kind of business. No, you won't need a calculator. No. I mean, you can bring one if you're like it gives you like a little like support, I guess. But I don't think I know. What's that? A blanket's, well, it depends. Don't write anything on it. I don't want you like hiding your head under the blanket. The TAs will be telling me all the weird stuff you guys try to do to cheat. Nobody's going to cheat, I know. All right. Actually, and sadly, we won't need to go into there. OK, so let's see. Find the bugs. You will have to write some code. As I said, there's a fair number of coding problems on there. It's not a lot, but it's a fair number. Short, nothing drastic. I am not going to take off points for like syntax errors. I mean, if you miss every semicolon, I'll probably take off a point because you're like, come on, this is C++, right? I mean, try to do the best you can with the syntax, but if you get something slightly wrong, I'm not going to worry about it. Now, if you miss a bracket, like for the delete, yeah, I'll take points off of that because that's kind of important, right? But missing like a semicolon at the end or spelling something wrong, I mean, I don't care, right? Those are things that the compiler would find instantly. So don't worry about that so much. Let's see. You have to explain what some code does, right? Like I might give you some code and say, hey, what's going on here, right? Just explain what's going on. You have to determine big O bounds. This is kind of an important one, right? We've talked about this every class so far. Asymptotic behavior. Is it constant behavior? Is it ON? Is it ON squared, et cetera? You should be able to figure that out for both. I'll show you some examples, but for both program code, easy program code, and for like when I write out a formula. You'll see. I'll give you examples about that. OK? And then some C++. I mean, I might say, why do we need a destructor? Right? And it's all the stuff we just talked about. Sometimes you have memory that needs to get deleted after the function or after the when the class is getting destroyed. OK? Questions on the types of problems? Yes? Oh, yeah, good question. Possibly. So I might give you a type of data structure or abstract data type that is similar to something we've seen. Like I think I mentioned this in class. There's a thing called a DEQUE, a DEQ, which is a double-ended queue, right? Which means you can remove from the front and from the back. So we haven't really talked about that, except now I mentioned it. But we haven't really talked about that. But I might say, hey, there's this thing called a double-ended queue. It allows you to remove from the front and the back. Write the remove front function, something like that, right? So not anything hard. I mean, there have been examples in previous iterations of this class where they've asked data structures that people have never heard of. They give them a little bit of information, expecting them to do all the code for it. I will not ask you that much. Again, I'm not trying to trick you on these. Okay? And by the way, I know like finding bugs is hard, and I know some of the coding in the fly is hard. You know, in real life, it's rare that you have to. It's not rare that you have to code under pressure, but it's rare that you have to code like right in the moment while people are staring at you, right? The only real example of that is in interviews, which are important, but you know, not real life in the sense of like your day-to-day job. You can do that. There's a really great article about NASA coders, like people who write code for like, well, used to write code for the space shuttle, right, and other satellites and things. They have to be really sure that there's no bugs. Right? Because you don't want the space shuttle like plummeting off into, you know, the atmosphere and burning up, right? Sadly, it's happened. But you don't want those kind of bugs. They haven't been software bugs. And so NASA coders, they have lots and lots of like teams that go and try to find bugs, and people write bugs. The average NASA coder, do you know how many lines of code the average NASA coder writes a day? 5 lines of code? 1 or 2? It's about 5, yeah. It's like between 5 and 10 lines of code a day, right? Because they've got all these other things that are going on. They really have to do it right, right? So they are not a pressure coding kind of place, right? I mean, your startup that's trying to beat some other startup, yeah, OK, they have coders that are like cranking out code all day. But then again, you end up with bugs, right? Not so good. So that's it. But anyway, point being, you will have to write some code, but it's not going to be particularly hard. And really, it's not real life. No. All right. Here's the topics that we've covered so far in class. Talked about C++, obviously. Arrays, linked lists, recursion. This was a big one, right? Recursion happens a lot in a bunch of different data structures. Can happen in a bunch of different data structures. Stacks, queues, and trees. And then this should not be a C. This should be its own. It should be 8, but asymptotic notation. OK? You'll have to know something about all those. Question?
Will there be any questions on Eclipse?
No questions on Eclipse. No questions on the UNIX tips. Hey, here's a question for you. How many people are like actually using Eclipse? How many of you are like glad I kind of suggested making you use Eclipse? Not all of you. How many people are not? How many people are using anything else except Eclipse? Actually, it's fewer people in here than the other section, believe it or not. Next semester, I'm still debating whether I'll have them do Eclipse again. I think it does have a pretty good debugger in it. And once you start using that, you'll be happy I made you do that. OK, so no questions on that, to answer your question. Danielle, no problem. Danielle, right? Yeah, OK. Let's see. Let's go through each one of these briefly. I'll give you some sample problems. For C++, so by the way, if you looked at the last semester's test, I went over one of the questions was on operator equals overload. You will not have to know that. We didn't even cover it in class. And I decided to take that out of the curriculum because it's, I don't know, not really. What's that?
What about cache friendly?
Cache friendly? I could ask things about something being cache friendly, right? I mean, if you have which is better for the, you may have not remembered this from class. Which is better for the memory cache, dynamic arrays or linked lists? Dynamic arrays. Why? Because everything's in order, and the cache, I don't know if you remember this, but the cache actually takes pieces of memory at a time and puts it into faster memory and so forth. So yeah, you might have to know a little bit about that. Not much, a little bit. Just a little bit about that. OK, we had already talked about this today. Dynamic versus automatic memory. Automatic memory is when you don't use the new keyword. Dynamic memory is when you do. OK? What's the difference between an abstract data type and a data structure? What do you think?
The data structure is kind of like defined by the programming language you're using or the tools you're using, and the tools already like include everything that you can do.
Give me an example of a data structure.
A struct or an array.
OK, I'll buy both those. An array, sure. And yeah, I mean, I like array.
Data types. Yeah, you're right. Data structure.
What else? There's one other big data structure we've talked about. Linked list, right? That's a data structure, right? Because it's like one node and another node and another node, and that's like the low-level stuff. OK, so what's an ADT, or abstract data type? Yeah, Jane. There you go. So an ADT, you can implement it using lots of different data structures. But what does an ADT normally define? Yeah, in particular. What were you going to say back there about ADTs? You're right.
Oh no, I was gonna say for like the data structure, I was gonna add a linked list, and then I asked a question, but I think I may have answered it for myself. But like, and then struct and class, those kind of things, they just be typed.
Yeah, they're well, kind of. Yeah, you can consider them as types. Yeah, they're not. I mean, that's like language dependent stuff, right? Versus a dynamic array. An array is not really a language dependent. Kind of is, but in general, that's like the base memory, and we call that, that's a data structure because it's an array. Yeah.
And a tree, would that be a data structure?
Tree's a tricky one. Tree's a little bit of both. I would consider tree a data structure because it's got a struct with no, like a binary tree as a left and a right node, and that's a data structure. Some people might say, well, look, it's defined by what functions you can do on it. You can make it with a linked list if you wanted to. You could make it with, so it's a little bit of a gray line there, but I wouldn't make you like define that one, which one that one is. Yeah, good question. OK, so that's the difference between those two. Good. All right, let's move on. So a C++ sample question, explain when a destructor is necessary. Right? When is it OK to use a default destructor? What is a default destructor? Max?
I'm going to hazard a guess and say it's what C++ supplies if you don't allocate any memory to it.
It's what C++ supplies. A lot of times, we will write a default destructor anyway, because I like to write a destructor just to say, to remind myself, do I need to write a destructor? Right? A default destructor would be something like this. Q, let's see. There we go. Right? It's just, there's nothing in there. It's just that, and when would you not have to do anything in the destructor? If there's no dynamically allocated memory. If you never use the new keyword, you're not going to have to do anything in the destructor to remove anything, like to delete anything. So that's the default destructor. When's it OK to use default? When you don't use new. OK. All right, static and dynamic arrays. We've kind of gone over a bit of this today. How would I define a static array with 10 elements? An int static array called bunny with 10 elements. How would I define that? Int bunny bracket 10 semicolon. That is a static array. OK, static because you can't change the size of that. Right? There's no way to really go about changing the size of that without doing funky things that you don't want to do. Right? If I wanted to do a dynamic array, right, it's the same thing. Int, I guess it would be actually, you can do the same thing. NNY, oh, no, sorry, int star bunny, and then equals new int 10 or whatever, right? Capacity or whatever you want. OK, that would be a dynamically allocated array. OK? All right, let's see. What's great about arrays? Constant time lookup. You can index into an array exactly where you want to go. That's great. Why are arrays good? What can you do in arrays if you have them sorted? That's cool. Yeah? You can add to an at the end. You can add an element to the end. But if it's a sorted array, what can you do to like search for things? Yeah. You can do a, what's that kind of search is that called? Binary search, right? You can do a binary search in an array because you can go to the middle, and you can go to the middle of the middle, and you can go to the middle of the middle of the middle, right? You can do that. So that's probably a good thing about array. What's the downside to using an array? There's a couple. If it's not sorted, it's hard to, I mean, you got to search through it. That's true. What else? Yeah, inserting in the middle is not fun. Or doing something in the middle, sure, because you have to move things, all the other elements, right? Do you have to do that with a linked list? No, you find the array, or you find the link you want, and then you just insert, and it's not, you don't have to do any big moving. There you go. You have to know how to expand dynamic arrays. We've done that in like 6 different programs so far. You have to know about the asymptotic behavior. What's the asymptotic behavior for inserting at the end of a dynamic array, appending to a dynamic array? Constant. How about the beginning? Linear if you have to move them all. Sure. What about the asymptotic behavior for searching through an unsorted dynamic array? Linear. How about a sorted one? Log n, because it's the cut in half, cut in half, cut in half. Good. All right. So those are the kinds of things you need to know there. See what an example question would be. Write the append function for a dynamic array. Right? What's the first thing you do in the append function? Trick question. What is it? Check the capacity and do what if necessary? Expand. Yeah. Then you just tag it on the end. Easy. Yeah.
So for a question like that, would we need to also write the expand function? Or would we
Probably not. I would probably say just you would call the expand function or something like that. Yeah. Yep. Or you could just write it. Only takes 2 minutes to write. Oh, here's the other thing about the midterm. When the TAs say time is up, papers go down. And they'll give you like 5 minutes notice. They'll be like, in 5 minutes, we're going to say you're done. And then I want papers down. I don't want them telling me that the other day to stand there and like rip the page out of your hand. Right? Last semester, it was last semester. Maybe you guys are some of the culprits. In Comp 11, Professor Sheldon told me that one time he actually told students, like, he's like, look, the test is done. And then he like walked out with people still like writing. And they had to like chase after him and say, here, take my exam. And he goes, it's too late. Is that any of you guys? Might have been. Anyway, I don't know if he accepted. He gave him late points anyway. So don't do that. What's that?
I like that method.
Well, I mean, it's, you know, the other one was he had a box where you put the tests in, and he said anybody who puts the page in above this yellow piece of paper is 10 points off. And people were still writing. And he's like, look, that was 10 minutes ago. So you finish on time, please. If you should not need more time for this one, it's not that long. If you need more time for whatever reason and you can justify it, write on the top, I need more time, and we'll talk. And you can email me and we'll figure it out. Okay? But you should finish on time. OK, linked lists, singly and doubly linked lists. Well, we talked a lot about that in the last few weeks, right? Nodes, you have to walk through a linked list. They're tricky, right? Linked list operations, you need to be able to reason through them. Like the whole point about keeping a previous or deleting, you know, what are the corner cases, right? If it's at the head, that's a corner case, right? So you need to be able to figure that. Deleting a node in a single, yeah, previous. Okay. All right, we've done lots of that. Doubly linked lists, pointers forward and backwards, right? And this is good and bad. It's good because you don't have to do things like you don't need a previous node. Bad because you have to think about all the details, right? It's a little tricky thinking about the details, as you guys found out for one of the labs. Circular linked lists are where the tail just points back to the head. Things like that. Pretty simple stuff. We've gone through it lots of times. Here's a good question. Find the errors in a linked list implementation for insert before. So I might say, here's insert before. You find the errors. Tell me what's wrong. And fix them. All right, we also talked about recursion. So I just posted a post on Piazza that had the solutions to the tree recursion problems that we did the other day. You can go look at that. You might want to like review that. Okay. Recursion is not magic, right? It calls itself. Recursion is very tricky for a lot of people. I have a tough time with recursion. Like thinking things through in a recursive way is difficult. And maybe it's just that I never got good training in it or something, but it's hard, right? I understand that it gets a little bit hard. But it's nothing magical about it. Sometimes it's very beautiful, nothing magical about it. You will have to think about you will have to write a sample or a simple recursive function. Nothing extensive, not really simple. I mean, like probably not as simple as, what is it, b to the n or whatever. That was an easy one, right? But a little bit more advanced than that, but recursive function. We talked about lots of examples. Fibonacci sequence. What was wrong with the Fibonacci sequence? Problem? Yeah.
You ended up calculating the Fibonacci of 2, like,
yeah, you ended up redoing your work, right? And the asymptotic behavior for that one was what? Exponential, which was terrible. You don't want to do that. Okay? Anyway, that's recursion. Have to do a little bit of that. Write a recursive function to calculate the sum of the first n even numbers. Oh. Might be a little tricky, right? A couple different ways of going about that. Not impossible, but it's a little tricky. You might want to think about that one. Okay. Remember, recursion is just basically a stack operation done for you. Because every time you call a function, that function gets put, the one you're calling from gets pushed onto the stack. You can talk about how they're very similar that way. Okay. Questions on recursion? No. All right. We did talk about stacks, obviously. Stacks are very simple, right? They're fast, and there's lots of real-life examples that use stacks, right? I asked a friend of mine this week. This weekend I was in Seattle. This is why I'm really tired right now. I was in Seattle this weekend. Got back at 7:30 this morning, and that's why I have a haircut too. So I'm in the Navy this weekend. But I asked one of the guys I work with in the Navy is a computer scientist, and I said, what's a real-world example for a stack? And he said, if you're modeling pancakes. I'm like, well, OK. I guess that counts. So can you say that on the test? Well, I probably want you to tell me what you're talking about. Like, explain a little bit more. You can figure out a real-life example using a stack of pancakes, sure. So stacks are last in, first out, right? Who is the person here that told me that the first in, last out behavior was, maybe it was the other class, I think it was the other class. Somebody in the other class said first in, last out is, you can't necessarily define it that way. It's always last in, first out. We had this discussion this weekend, too. It was a nerdy weekend, I guess. OK, stacks have 3 operations that we care about: push, pop, top. There's one more that I guess we care about. Is empty. Yep, is empty is one. We can do lots of stuff with stacks, postfix notation. I won't make you convert infix to postfix. That's hard. But you could if you had the algorithm, I'm sure. And tree traversals that you will do in this week's lab. Tree traversals are most of them you can do with a stack. Not all of them. Most of them you can. Okay. All right, so let's see. Sample questions. Explain the stack functions and how they're used. OK, like how do you use, what's pop, how does pop and push work? How do they work? Explain how to use a stack to do a post order traversal. We talked about that. Discuss the asymptotic notation. What's the asymptotic notation for push? Or what's the asymptotic behavior for push? Constant. What about pop? Constant. What about top? Constant. Is empty? Constant. That's why we use it, because everything's constant, right? It doesn't. You work for all different types of problems, but it's a pretty good one there. Okay. All right. We also talked about queues. Right? Queues have this first in, first out behavior. You guys are getting sick of queues because of this week's assignment. Insert at the end or the back. Remove from the front. Very similar. So in this week's lab, it's so similar that sometimes we don't call it in Q and DQ. We actually call it push and pop. Why? Well, that's just the way they wanted to make it similar to the stack in that sense. They do call it front instead of top. Right? But in Q and DQ is normally what we call it. Okay? Why don't you need to move elements? When you do DQ, why don't you have to move the elements back and forth? You just move the indexes, right? Not really pointers in our definition, but you just move the indexes, and then you keep track of where the front and the back are, and you don't actually need to move them. So that's cool, right? Circular queue is useful. We already talked about that. If you don't have a circular queue, you end up walking down the queue and then having to expand too often. So we can do better than that. And if you want to do level order printing, you need a queue. We mentioned that, and you'll practice that in the lab this week. OK? All right. Questions on queues? Like I said, you're probably pretty sick of them at this point. Write the enqueue function for a circular queue. What does enqueue do? How do we do enqueue? Add to the back, and then move the back, and then, if necessary, well, we also increment the, well, sorry. Yeah, we also increment the size. And if necessary, we wrap it around, right? Not bad. OK. Then we finally talked about trees last week. Trees are our second node-based data structure, right? You should know all these tree vocabulary words, but this is what goes on your cheat sheet, right? I mean, you put like the height of the tree is the number of nodes to the bottom, et cetera, right? Children, parents. I'm not going to ask you about like grandparents or cousins, second removed, and all that, but you should know how to calculate these. For trees that are not binary trees, we could have links to all the children, but that's hard to implement, and it would involve some other data structure, right? So we can do something interesting where we say, hey, we do this first child, next sibling business. You should go review that. Review the first child, next sibling thing for trees. It's asymmetric, so it's a little wacky, but works for file systems pretty well. Trees, recursive programming are good. We saw those examples for tree recursive programming. Okay. All right. We also talked about binary trees, of course, right? And binary search trees. Binary trees, obviously nodes with two children, left and right, that's it. We can implement a node that has a left and a right pointer and some data. Binary trees can easily degrade into linked list behavior if all the nodes are one direction or the other, right? If you only have one child, then you end up kind of behaving like a linked list. We did talk about binary trees for arithmetic, right, with a plus and then the a and b on one side and so forth. We also talked about using a stack for postfix notation, and we didn't really talk too much about this one, but that's you can do that with a tree. Trees, you will practice this tonight and tomorrow. In order, pre-order. You won't practice post-order, but it's really simple if you know the other ones. And level order. Okay. All right, let's see. So the binary search trees, this is the one that's a really special tree, and it's awesome, right? It's got this invariant, right? The invariant says everything to your left is smaller than you. Everything to your right is bigger than you. End of story, right? That's the invariant. We know for a binary search tree, if it's random binary search tree, the average depth is log n, which is great because it means searching through it is fast, right? You need to know how to do find min, find max, contains, insert, and remove. Remove's the hard one, right? What was the algorithm we landed on for remove? I'm gonna have to make you all like talk to your partner for 5 minutes and figure it out again. What was it? Yeah, Erica.
Isn't it that you go into the right side of the tree and you find the lefternmost node of that, and then you make that into you replace the root with that?
OK, yes, mostly. OK, so if you're removing a node, if there's three cases, right? Case one was if it was a leaf, and that was easy, just remove it. Case two was if there was one child. That was easy, you bypass it. Case three was if there were two children. That's the one that you're talking about, right? If there's two children, you go to the rightmost node, or you go to the right child, find the minimum, which is all the way left, left, and then you replace that one with the one or you swap that one with the one you want to replace, or put that one with the one you want to replace, and then delete that one. So it's pretty simple algorithm when it comes down to it. Okay, you should know how to do it though. We didn't talk about this. So lazy deletion, I won't ask you a question, but for what it's worth, lazy deletion is if you have a tree and you don't want to go through that delete thing, you just want to mark the node as being deleted. That's one way to do it. You just say, hey, I've got another field in my node called deleted, and you just check it. Or you set it to bool equals true, and then it's deleted. And when you get to it, you skip it. And you say, this isn't really here. What's nice about that, let's say you were going to insert and delete lots of times the same nodes. You just go, and instead of having to reinsert or remove every time, you just check and uncheck that little Boolean value. So it's kind of nice to be able to do that. It's called lazy deletion. And you'll see that in some bigger trees sometimes. Okay. Questions on binary search trees? No? Describe how to insert or delete from a binary search tree. Which is harder and why? I would also ask you, what's some of the asymptotic behavior of a binary search tree? It's always logarithmic. Well, not always. Right? It can be worst case and best case and worst case, yeah. Right? To find in a binary search tree, what's the average case? Log n. What's the worst case? Linear, order n. And what's the best case? Constant, because it's right at the top. Good. OK. And then finally, through the whole class, we've been kind of talking about this big O notation. OK, I think I've hammered it for every object we've talked about so far, right? This is fundamentally how we compare things, right? We want to be able to say, here's two algorithms. Tell me why I want to use one or the other. That's what gets you paid in software development, choosing the right data structure, right? Or the right abstract data type. Right? That's how we compare it, using asymptotic notation. Which one's going to be slower? Which one's going to be faster? Sometimes we want to get a little down into the weeds and compare those primitive operations. Basically, you just say everything's 1, and then you just count it, and then count everything up, and then do your analysis. You don't worry about constants. We don't care about constants. We just ignore them, right? And when you take algorithms class, you'll start worrying a bit more about constants. Right? We only report on the fastest growing, the slowest growing functions. I should say slowest growing. Slowest growing functions. In other words, the ones that are going to take the longest to run is the ones we want to report. I'll show you an example in a sec. You should be able to order the functions. If I gave you 3 different functions, you should be able to say which one's going to be asymptotically fastest, middle, and slowest. OK? Not that hard. Just be able to do it. Here's the big ones we talk about. This one's the one that we haven't really gone over yet. This one will come up when we talk about sorting later. When we get into sorting, which is in a few weeks, we'll talk about n log n behavior. But these are the ones I really care about, right? Constant, logarithmic, linear, quadratic, all other polynomials except quadratic, cubic, quartic, all that kind of stuff. And then this horrible exponential one. Heat death of the universe one, right? OK? Those are the ones we care about. Some hints on those. Remember, constant does not depend on how many you have. If it's constant behavior, it doesn't matter if you have 1 million or 1. You're going to get it instantly. Linear means you have to access all of them, right? N squared is this nested loops, 2 loops, a loop inside a loop. Log n is where we can break things into half, 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 or a third, 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 et cetera. Okay? Not particularly hard. Yeah, Isabella? I'm not going to ask you to write down the exact ones. No, I might give you some code and say, what's the overall asymptotic behavior? And you have to read through it and figure it out. Just ignore most of it. I mean, you just find the parts that matter. And then I know that's the hard part, right? Finding the parts that matter. But that's you won't have to actually write out the whole thing. No. You can do that in algorithms class when you get there. All right. OK, so here's a sample question. Well, first of all, you should be able to analyze all the algorithms we've talked about, which we just went over most of them, right? As far as asymptotic behavior. You should be able to determine the asymptotic behavior for a function. What's this one? What's the asymptotic behavior of this one? Yeah, if I said O, what would it be? O what? O n squared. Right? What if I made that 25 million n squared? Still n squared. Now, in real life, the 25 million would probably start to make a difference. But the n squared is the one we care about. So you don't worry about those ones. It's just n squared. Easy. OK. All right. I believe, yes, that is it. Are there last-minute questions on the midterm, homework 3, anything else? OK, I will see you guys in lab and then not on Wednesday. But good luck. If you have any other questions, put them on Piazza.